Tanks do not fill up at ordinary gas stations. But if the M1 Abrams had to, it genuinely would not care what was in the pump. Under the hood, it is not a typical tank engine. It is technology borrowed from jet aircraft. That is why it burns dozens of liters of fuel before the tank moves an inch, just at startup. This seems like an engineering mistake, but the US Army did not just accept it, they bet everything on it. Why? The engine in the M1 Abrams is called the AGT-1 500. It produces 1,500 horsepower and a torque of around 3,750 Newton meters. But those numbers are abstractions. Here is what they mean concretely. The Abrams, in its M1A2 variant, weighs approximately 63 tons. The AGT-1 500 pushes those 63 tons to 72 kilometers per hour on flat ground. Over rough terrain, it is slower, but still staggering. For comparison, an average truck carrying the same load would move at half that speed with an engine twice the displacement. One more number. Starting the turbine by itself, before the tank has moved a centimeter, consumes around 40 liters of fuel, just to turn the engine on. The Abrams carries 1,885 liters total. Its documented cruising range is around 426 kilometers on road. That is roughly the distance from New York to Boston, and there will not be enough to get back. This is a compromise, and it is entirely deliberate. Most people think the gas turbine in a tank is about power. Someone in the Pentagon decided to install the most powerful engine available, and this is the result. More horsepower, faster tank. Simple logic. Here is the problem. Power is not the primary reason. Most diesel engines of the same era produced enough output for a heavy tank. The Soviet V-84 and the T-72 delivered 840 horsepower, less, but not critically less, for a 44-ton vehicle. The British Challenger 1 had a Rolls-Royce CV12 diesel, making 1,200 horsepower, and fought effectively in the same conditions. The real reason is something else entirely. A turbine has one property that no piston engine possesses. It runs equally well on diesel, aviation kerosene, gasoline, and even mixtures of these fuels, with no adjustment to the fuel system whatsoever. This is called multi-fuel capability. In conditions of logistical chaos, when a column is cut off from supply bases and has to take fuel from whatever is nearby, this is not a convenience. It is survival. The gas turbine in a tank is not about power. It is about logistical independence in conditions where the supply chain gets cut first. Before discussing the engineering, one person needs to be named, because the AGT 1500 has a specific author. Dr. Anselm Franz was Austrian, a mechanical engineer. In 1939, at the start of the Second World War, he led development at Junkers of the Jumo 004, the first serial production turbojet engine in history. The Jumo 004 powered the Messerschmitt Me-262, the first jet fighter to see combat. Around 6,000 of these engines were manufactured before the war ended. After Germany's surrender, France was brought to the United States under Operation Paperclip, the secret program through which Americans transferred hundreds of German and Austrian scientists before the Soviets could do the same. In 1952, he joined Avco Lycoming. There he developed the T-53, the first turboshaft engine for helicopters, fitted to the Bell UH-1 Huey, then the T-55, the engine for the CH-47 Chinook. From 1963 onward, the AGT 500, but there is a detail that almost never gets mentioned. The Jumo 004 on the Me-262 had a service life of 10 to 25 hours. Not thousands, just hours. The blades burned out, the bearings disintegrated, the metal could not withstand temperatures it was never designed for. Franz knew this better than anyone because he wrote the failure reports. When 20 years later he was designing the AGT 500, he did not begin by asking how to make it more powerful. He began by asking how to make it not fall apart after 20 hours. The AGT 1500 service life before overhaul, according to Army documentation, is 2,000 to 3,000 hours, 100 times more. This is not technological progress. It is an engineer's personal account with his own past mistakes. Now, the most obvious problem, and the least obvious solution. A gas turbine is essentially a jet engine without a nozzle. It compresses air, mixes it with fuel, burns it, and spins a shaft through the expanding gas flow. An aircraft has one luxury: it flies in relatively clean air at altitudes where there is no dust. A tank in the Middle East moves in a cloud of fine-grained sand, whose particles are smaller than a human hair. It does not settle, it hangs in the air. It enters the intake and turns the turbine blades into sandpaper. Literally, the blades erode. The clearances between them and the casing increase. Efficiency drops. Service life drops with it. This is like breathing through a cloud of flour during a marathon and expecting the lungs to hold up. The solution is a two-stage air cleaning system. First, an inertial separator, then a barrier filter. The inertial separator spins the incoming air, throwing heavy particles outward to the walls and ejecting them before they reach the compressor. It is a device that throws dirt out by centrifugal force and cleanses itself continuously. The second stage, the barrier filter, catches whatever made it through the first. The focus is cleaning. When American tank units moved into the Kuwaiti desert before Operation Desert Storm in 1991, the first documented problem was a shortage of these very filters, the so-called V-Packs. The first units of the 24th Infantry Division urgently requested 3,000 additional V-Packs on top of existing supplies, and it was this system, not the armor, not the cannon, that became the first logistical problem before the ground phase even began. But solving the AIR problem opened another one. The turbine burns fuel at temperatures exceeding 1,000 degrees Celsius at the inlet to the first stages. The melting point of aluminium is 660 degrees Celsius. Steel melts around 1,370 degrees Celsius. The turbine operates in a range where ordinary metals are already beginning to flow. How is this even possible? The turbine blades in the AGT 5500 are nickel superalloys with internal cooling channels. Compressed air, drawn from before the combustion chamber, is fed through these channels. It cools the blade from the inside, preventing it from reaching critical temperature. The DNA of this approach comes from the helicopter engines T-53 and T-55 that France also developed at Lycoming, and which went through Vietnam and proved their reliability in combat conditions. Not from fighter jets, from helicopters, from the Huey and the Chinook. But there is a consequence. The turbine generates a colossal amount of heat at the exhaust. In an aircraft, this heat goes into the nozzle and is pushed out the back. That produces thrust. In a tank, there is nowhere for it to go. The AGT 5500's exhaust exits to the right of the turret, and the gas temperature there can exceed 500 degrees Celsius. This is a thermal signature visible in the infrared. A diesel engine runs far cooler at the exhaust. On this point, the turbine fundamentally loses, and this is precisely where Franz did something found in no aircraft engine of that era. He turned the problem into an advantage. The AGT 5500 has a recuperator, a cylindrical heat exchanger surrounding the output shaft. Hot exhaust air passes through it and transfers heat to the compressed air that has already passed through the compressor but has not yet entered the combustion chamber. The result is the fuel no longer has to heat the air from scratch. The air enters the combustion chamber preheated to over 450 degrees Celsius. Fuel consumption drops by documented measurement to 226 grams per horsepower per hour. Without the recuperator, the AGT 1500 would have been impossible as a practical solution. This is not aircraft technology. Aircraft engines do not need a recuperator. They already achieve high efficiency through speed. This is a solution Franz created specifically for the ground. The sky provided the form, but the content is new. One more point that rarely gets mentioned. The compressed air the AGT 5500 draws from the compressor also powers the chemical and biological protection system. The turbine pressurizes the fighting compartment so contaminated air physically cannot enter. No diesel engine achieves this without a separate compressor. Here the turbine solves three problems with one airflow: cooling, fuel economy, and crew protection. Here's a paradox that breaks the assumption about why a turbine is good for a tank. A piston engine, a diesel, delivers maximum torque at low revs. It pulls hard from a standstill, exactly what a heavy vehicle needs when moving out of mud or climbing a grade. A gas turbine is the opposite. It delivers its maximum at mid and high revs. At low revs, it is weak, and if the AGT 500 were connected directly to the tracks through a simple gearbox, the Abrams would get off the mark poorly and burn even more fuel than it already does. The solution was the Allison X1100 3B hydrokinetic transmission. It contains a torque converter, a device that transmits torque through fluid without a rigid mechanical clutch. It automatically multiplies torque at low speeds, up to 3 times the input value, and smoothly reduces the multiplication as speed builds. The turbine made this possible because only a turbine delivers a sufficiently smooth power output across a wide rev range for the hydraulics to respond without jerking. The result, the Abrams accelerates from 0 to 32 kilometers per hour in approximately 7 seconds. For 63 tons, that defies physical intuition. There is one more side effect that rarely gets mentioned. The AGT 500 is extraordinarily quiet compared to any diesel of equivalent power. The sound of a turbine has a different frequency. It does not carry as far. This is why the Abrams earned the nickname Whispering Death. 63 tons approaching, and you hear them later than you expect. The nickname did not come from the desert. It came in 1982 during Reforger exercises, joint US and Canadian maneuvers in Europe. A column of Abrams approached Canadian positions undetected. The Canadians were expecting the rumble of diesels and heard nothing. After they were notionally destroyed, one of the Canadian soldiers gave the tank its name. By 1991, it had become the official nickname. An American armor officer who fought in the Gulf put it simply, "By the time you hear an Abrams, you are already dead." And here is the honest part. The AGT 1500 consumes fuel significantly more intensively than any diesel of comparable power. Documented consumption in combat movement is approximately 2 gallons per mile, while comparable diesels consume around 1 gallon per mile. The logistical chain for the Abrams requires more fuel trucks, more tankers, and more planning. During Desert Storm, in 1991, the AGT 500 burned around 300 gallons of JP8 in 8 hours of combat operations, and this became the system's primary vulnerability. Critics had been calling it excessively fuel-hungry since 1990. The driver mechanic who goes into the field with a tank rated for 426 kilometers, and who knows the real combat range will be half that, pays for this compromise personally every time.